Attention is all you need. You must have definitely come across this research paper that changed the entire world, and you must be knowing what standard attention mechanism means. And you must have also heard about the hype of gated DeltaNet. Qwen 3.6 and 3.7 models are heavily based on the gated DeltaNet architecture. So I'm going to explain you gated DeltaNet in short in a very simple manner. Standard attention is powerful, but it's like a student who rereads everything every time. Question number 1, maybe you got the answer from the textbook. But for the question number 2, rereads the entire textbook again, so it explodes quadratically. Standard attention is powerful, but it has one brutal flaw. It scales quadratically with sequence length. Think of standard attention like a student who rereads the entire textbook for every single question. Accurate, thorough, exhausting, and every new page you add multiplies the cost. As I said, it explodes quadratically. Every token attends to every other token. That is good for accuracy, but it needs unlimited infinite compute. But gated DeltaNet takes a different approach. It has a thing like notepad, a fixed size memory, and here's what makes it smart. Instead of rereading everything, the student remembers what he read and only goes to new things he needs. He is like a smart student, and standard attention is a very scholar but a dumb student. Scholar and dumb at the same time, because he's wasting his energy on the wrong things. Gated DeltaNet is like a very smart student who knows what needs to be done and where to utilize his energy. Constant memory and linear cost. Before writing, the student checks what's already there. If it's wrong, he writes only the correction, the delta, the difference, not the whole thing again. This makes the memory precise. Read what's currently stored for this key, compute the difference to the new value, write only that difference. That's it. When the topic shifts, say you move from one function to some another function, the gate closes on old irrelevant memory. So let's say your physics exam is done, and standard attention is like a student who keeps the physics exams thing in his mind while the chemistry exam is going on. It might be useful at some point, but it utilizes a lot of energy and it's not efficient. Old notes fade, new context comes in sharp, but gated DeltaNet had one problem, one major constraint that nobody was talking about. NVIDIA researchers just saw it and fixed it forever. In gated DeltaNet, there was a single scalar that was controlling two things that were not relevant to each other, deciding how much to erase old associations and how much to write new values. Is it even relatable? I might want to add up more stuff than I erase. Why should I erase the same amount of stuff that I write? It's just dumb. So NVIDIA researchers fixed it. Erase softly, you can only write softly. Does that even make sense? Absolutely not. So the gated DeltaNet-2 paper fixed it by replacing the one scalar by two independent vectors, WT and BT. WT is the vector that is responsible for writing new stuff, and BT is the vector responsible for erasing the old stuff. And they are not relevant to each other now. You can erase the gate 1, 3, 5, 7 while protecting the gate 2, 4, 6, 8. And you can write in the gate 2, 3, 5, 6, 8 while skipping the gates 1, 4 and 7. So erasing and writing is no more correlated to each other. And that is a very wise decision. Gated DeltaNet-2 will be even more revolutionary than the gated DeltaNet-1, the original traditional gated DeltaNet. It sounds obvious now, but the hard part was never the fix. It was noticing the constraint existed at all. So this is what the gated DeltaNet-2 architecture looks like now. A token enters in linear projections, QK weak query key value, decay gate, erase gate and write gate. Two different vectors. No correlation between them. And then the notepad thing and then the output tokens. Decay gate, channel wise fade. Each key channel forgets at its own learned rate. Topic shifted, old notes dim automatically. Erase, new. Vector over key channels picks exactly which old associations to scrub, independent of how much you write. WD, write, vector over value channels picks exactly which parts of the new value to commit independent of how much you erase. Amazing. Each paper fixed one thing. DeltaNet introduced the delta rule. Gated DeltaNet added scalar decay, so old associations fade away when context shifts. KDA, key delta attention, made the decay channel wise. Each key dimension forgets at its own rate, but beta was still one scalar. And Gated DeltaNet-2 by NVIDIA finally fixed that, spotted that beta was doing two different jobs, and both of them weren't correlated to each other. So they separated it. As simple as that. It sounds obvious now, but the hard part was finding the constraint, as I said. NVIDIA researchers did a very amazing job. So I explained you how standard attention and gated DeltaNet are different from each other, and what new things were added to Gated DeltaNet 2 from the existing Gated DeltaNet 1. That's all for today.